Hello everyone, welcome to video 2 of One-Way ANOVA. In video 1, we talked about the transition or leap from t-tests to ANOVA. And so we'll review that very briefly here. First, how does a paired sample t-test differ from a within subjects ANOVA? In this figure, here, we have a situation in which we would do a paired sample t-test. We have one group, and we're comparing two outcomes or two scores from this one group. So we have prejudice towards feminists and prejudice towards prostitutes. So in video 1, how did we modify this figure so that it would require, the situation would require within subjects ANOVA? Right, we added a third outcome here, prejudice towards lesbians, another predominantly female group that is socially derogated, socially maligned, looked down upon, along with feminists and prostitutes. Right? So we have one group producing 3 scores. Right, we're comparing more than 2 scores within the same group of people, hence a within subjects ANOVA. So the leap here from the paired t-test to the within subjects ANOVA is pretty simple. Just like the leap from the independent sample t-test to the between subjects ANOVA. So in this figure here, this situation will require an independent sample t-test where we have 2 independent groups, liberals and conservatives. We're comparing these 2 independent groups and one outcome, one DV here, feminist prejudice. And so how do we change this figure so that the situation we require a between subjects ANOVA? We added a third group. We added political moderates. So now we're comparing more than 2 separate independent groups on one outcome. So we're comparing liberals, moderates, and conservatives on their levels of feminist prejudice. So we're comparing more than 2, right, independent groups on one outcome, or you can say that we're comparing one outcome between 2 or more independent groups. So the leap from doing an independent sample t-test to a between subjects ANOVA, again, is, I think, pretty simple conceptually. But as I said in the last video, I think the leap from the conceptual leap from a t-test to ANOVA is pretty simple. But when we actually get into the output, things seem a lot more complex than is laid out here. So before we get into that SPSS output, there's still some things that we need to go over. And so we'll focus on the between subjects ANOVA here, although a lot of the points that we're going to go over here apply both to the between subject and within subjects ANOVA. But to just help contextualize our discussion here, we'll talk about the between subjects ANOVA lecture example here. And again, we're comparing liberals, moderates, and conservatives on their levels of feminist prejudice. So let's first talk about what we predict to happen. Right? So how will liberals, moderates, and conservatives differ on their levels of feminist prejudice? Well, we already know, we already have examined the difference between liberals and conservatives and their levels of feminist prejudice. So if you remember back to when we conducted the independent sample t-test, conservatives reported a lot more feminist prejudice than liberals. And so we're going to illustrate that in this figure here. And again, you can see that we have prejudice towards feminists on the y-axis here. And then on the x-axis, we have our independent variable, political orientation, and our 3 independent groups, liberals, moderates, and conservatives. And so we're going to place dots here to represent the mean scores for liberals and conservatives. So liberals' score was around 4, conservatives was around 6. So what would we predict to happen with moderates? Where would we place this dot here for moderates? You may think, well, moderates are politically supposed to be sort of in the middle, right, in between liberals and conservatives. So you may predict that they will fall in between, in the middle of liberals and conservatives. That's reasonable. That's logical. And so if we connect these dots with lines, now we have a line graph. So this is a new graph here, presenting a new graph, a new way of representing mean differences between groups. We could easily have a bar graph here where we have bars representing the mean score for liberals and the mean score for moderates and the mean score for conservatives. But line graphs are going to be really helpful when we transition from one-way ANOVA to two-way ANOVA in probably a couple weeks. So introducing the line graph here. Now, we're going to conduct a between subjects ANOVA to examine the differences between these three different groups. But it is totally feasible to conduct a series of independent samples t-tests to compare these three groups. So how many t-tests, independent samples t-tests, would we need to conduct to compare all three groups here? Right, so we would need to conduct a t-test to compare liberals and conservatives, liberals and moderates, and then finally moderates and conservatives. So we would actually need to conduct three different independent sample t-tests if we're going to compare all three groups. But there's a problem here. And the problem is with type 1 error. So for any given t-test, for any individual t-test, what is the percentage chance of making a type 1 error? And you're probably thinking to yourself, like, I don't know, Dr. Webster, I really don't know. So let's go through this question. First, we have to make sure that we revisit what is type 1 error. Type 1 error, right, is one of the two errors, right, that we can make in inferential testing, right? Type 1 and then type 2. Type 1 error is when you conclude that there is a difference, right, based upon a p-value, when in fact, if you actually got everyone from the population, there wouldn't be a difference, right? And that's different from type 2 error, in which we conclude based upon the p-value that there is no difference, when in actuality, if we got everyone in the population, there actually would be a difference. So here we're talking about type 1 error, when we're concluding that there's a difference when there actually isn't. And so we have to think, okay, when we conclude that there's a difference when there actually isn't. So what is our criteria for concluding that there is a difference, right? We're talking about significance here, right? And so what is our criteria for significance? What makes a significant difference? What makes a difference significant? Well, that's based upon p-values, right? So if our p-value is less than or equal to 0.05, right, there's a significant difference, that we are confident enough that the difference between those two means is far enough away from zero, right, that those two means are far enough away from each other that it's likely a true and real difference. So for p-value, for setting our threshold, our criteria here for 0.05, that means we're going, that means we're at least, right, 95% confident, right, that those two means are really far enough apart to suggest a true difference. And so for 95% sure with our criteria of 0.05, that leaves a 5% chance of being wrong. Right? So there's a 5% chance of making a type 1 error for any given t-test. But the thing is that we would need to conduct 3 independent sample t-tests to compare all 3 groups here. And we can't consider those 3 t-tests as sort of independent from each other, right? So we'd actually need to take the number of t-tests needed, 3, and multiply that by 5%. So 3 t-tests times 5% equals 15%. There's actually a 15% chance that we will make at least one type 1 error in the group or family of comparisons here. That 15% chance is a family-wise error rate. So these 3 independent t-tests that we would need to conduct, that's a family of tests. They are related in that they all belong to the same independent variable, political orientation. Liberals, moderates, conservatives, they're all under the same independent variable here. So hopefully some of that made sense, right? Bottom line is that you need to know that for any given t-test, for one t-test, the chance of making a type 1 error is 5%. But if we're going to compare different groups under the same independent variable, then we need to multiply the number of tests needed by 5% to get our family-wise error rate, in this case, 15%. Right? And so ANOVA keeps type 1 error rate at 5%. So that's good. The other advantage of ANOVA is that having everyone in one test better estimates the error term and S pooled. If you remember, for any inferential test, it all boils down to observed difference divided by error. And we discussed how sample size affects the error term. Right, the more people that we get in our sample, the more people that we're drawing from our population, that decreases our error term. Right? Conceptually, this makes sense. As we get more people from our sample, as we get more people in our sample, more people from the population, we should have a better feel of what's actually going on in the population. We should have a more accurate, better estimate of that error term. Right? And error is, of course, based upon standard deviations, right? And so as we get more people in our sample, we'll better estimate the standard deviations, better estimate our error term, and S pooled. So we are going to use S pool to calculate our Cohen's d values for the mean differences with ANOVA. And so yeah, so having everyone in one test, liberals, moderates, and conservatives all in one test, we're going to have better estimates of our error term and S pooled. And so these are the two major reasons why ANOVA is advantageous to doing a series of independent t-tests. ANOVA keeps the type 1 error rate at 5%, and ANOVA better estimates the error term and S pooled value. So before we start to look at SPSS output, let's talk about sort of the general approach to interpreting ANOVA. All right. So ANOVA produces F values, not T values. So if you remember, the two steps for any inferential test is we first calculate the inferential value. And so for ANOVA, we have an F value. For a t-test, we have, of course, T values. I don't know who decided that ANOVA would have F values and not like A values. I don't know. But here we have F values, right? And so F values range from 0 to positive infinity. F values cannot be negative. If you get a negative F value in SPSS, something went terribly wrong. And then with any inferential test, right, we calculate the inferential value and then we find the associated P value. So for every F value, we're going to have a P value. And so what ANOVA is doing is that it is evaluating the differences simultaneously between all the groups. And then the P value that we get with the ANOVA test will let us know if there's at least one difference between the groups. So if we get a significant F value, if our P value is significant, there's at least one significant difference between the groups. There may be two, maybe three, we don't know, until we look at what are called the post hoc tests. So if we get a significant F value, then we look at the post hoc tests. SPSS also calls them multiple comparisons. So we have another case where we have two terms for the same damn thing. So when we're looking in SPSS output, or if you are in SPSS, post hoc tests are the same as multiple comparisons. Right? And so these post hoc tests or multiple comparisons will identify specifically which groups significantly differ. And if you go into SPSS and you're running a one-way ANOVA, you'll actually, when you hit like the post hoc test option in SPSS, you'll get a list of like over 20 different post hoc tests. The one that we'll use in this class is called Bonferroni. I know it sort of sounds like a pasta, I'll take some bonferroni with meatballs and extra Parmesan cheese, please. But in this case, bonferroni is the name of some statistician that created a post hoc test. And bonferroni test best corrects for type 1 errors. It's one of the safest post hoc tests that you will do. No statistician should quabble with you if you used bonferroni. Because the type of post hoc test really varies between discipline, but in psychology and the behavioral sciences, bonferroni is one of those that sort of reigns supreme. So I'm going to stop there for now, and then in the next video we'll start to get into some output. Yeah. So until the next video, bye everyone.